Okay, I'm sharing the
You're seeing
kind
it.
of whiteboard. Can you see that? This is
Got it. And it's the right size for us. We can see the whole.
okay. So that was the last time. Let me know when you want me to start, and I will go.
I think we are pretty much ready here. So we'll kick things off with the third and final lecture by Martin Kruczenski on applications of the Bootstrap to the simple systems aiming at QCD. So Martin, please take it away and tell us about the Bootstrap.
Okay, thank you. And once again, I want to thank the organizers. It seems that it's a very nice workshop with a lot of discussions. I think I could have learned a lot if I was there, but okay, not the first time that COVID spoils my plans. So hopefully I could visit some other time. One second before I start, I wanted to say a couple of things. One is that together with Joao Penedones and Baldwin Rees, we wrote one of these snow mass papers on this topic. And for if that's archive number is this. So for the students, if you're not aware of these snow mass papers, they are short papers with a description of state of the art of some subtopic and some vision for the future. So I strongly recommend you look not necessarily at our paper, but if you are interested in some topic, look at the SNOMAS paper on that topic in high energy physics or particle physics, and you will usually have a nice description of what people are thinking about on that area. And this is not just sort of our vision. We try to ask everybody working on this topic. In particular, I want to mention Aninda Singh, who gave us some advice on what to write, and he's there in Bangalore. I'm not sure if he's attending this, but I guess you probably will be very happy to answer questions on this topic. That's one thing. The other thing is that all these things I'm writing here, the computer is saving them in some PDF, so I will send it to the organizer together with the slides if you want to look back at some of the things I wrote in case you are interested. So that's okay. That's what I wanted to say. Now let's do a brief review of what we said last time. We were talking about positivity as an important constraint. And we said positivity, and we said that the S matrix has a positivity condition. Then we derive with these in and out states. So let me derive it in a slightly different way. So suppose I have the S matrix, which is unitary, and I have a subspace D, and then I have the rest. So I'm gonna call this SD, and then I can put S1, S2, S3, and I multiply by the dagger. I have to get identity, and in particular up here I get SD dagger plus S1 dagger, and I get some other stuff, and this should be identity, and that means that SD in the subspace SD dagger plus S1 dagger should be identity. And one can write this by saying, okay, SD dagger minus the identity is equal to minus S1 dagger. And when I take, as we already said, a matrix times its dagger is positive definite. So with the minus is negative definite. So this matrix is negative definite. And that's equivalent to what we said, that 1 SD dagger 1 was a positive definite. You can easily convince yourself that's true. So, and this is the positivity condition basically where we are always using for the S matrix. Another comment is that the space, sometimes I move too fast. I don't know if you are taking notes. The idea is just this is negative definite. The other thing, what I wanted to say is that the space of positive definite matrix is convex. And if you intersect a convex space with linear constraints, for example, analyticity, crossing, and other symmetries, the space is still convex. And that's why this space of allowed S matrices that I was plotting, it was always a convex space, and convex spaces are easier to deal with. So why is it convex? Because if I have a matrix S1 and another matrix S2, well, maybe S is bad name here. I'm not thinking about the S matrix. So let's say a matrix A1 that is positive definite and a matrix A2 which is positive definite. Then if I take a number between 0 and 1 and I make this linear combination, the claim is that this is positive definite, and the proof is very simple. I take the mean value in some state V, and then I get alpha V A1V plus 1 minus alpha V A2V. And this is positive because this is positive, because A2 is positive definite. This is the same. And both alpha and 1 minus alpha are positive because of this. That means that space of positive definite matrices or semi-definite is convex. So if 2 points are in the space, the segment between the 2 points, which is this, is in the space. And that simplifies things. And when you maximize linear functions and so on, all these programs that I was mentioned before take a large advantage of the space being convex. Okay, so now the idea of today was to discuss QCD. So what do I mean by QCD? Is, for example, an SU3 gauge theory with 2 flavors with the same mass. At low energy, we know numerically and from experiment develops a mass gap and reduces to a theory of pions. And we would like to understand the S matrix of the scattering of pions that should have, for example, resonances like the rho and other things like that. Now, before you ask, obviously, how we solve QCD, no, we have not done that, but maybe there is some hope. The other obvious question is why would this work if it didn't work in the 50s and 60s? The advantage we have are twofold. One, we have better computers and also importantly, better algorithms that have been developed to study these spaces. And we also know the underlying field theory. So in those days, in the old days of the Bootstrap, they didn't know if it was a quantum field theory or what kind of theory was behind the strong interactions, and they wanted to use the S-matrix Bootstrap to compute it, ignoring the microscopic theory, if you want. But still, it seems to be a tall order to do this. So what would mean solving QCD will mean that if you have some SUN gauge group where somebody gives you the N and they give you some number of flavors, then you can compute the S matrix of the corresponding low energy mesons. What's the difference with the standard low energy effective theory? Well, it's basically the same, only that when you put a low energy effective theory, you write a Lagrangian, and you don't necessarily impose all the constraints from unitarity, analyticity, and all that. And one approach will be to write the low energy effective theory and put constraints on the couplings from this Bootstrap, and that's what Rastelli was doing in this paper we mentioned last time at the end. Or more like I was doing in 2D, just try to write the S matrix, and that will have all the constraints incorporated. So it's a more ambitious or more complete form of way of doing the low energy theory, if you want. Okay, so historically there was some nice observation that let me repeat it because I think it was one of the basic ideas that was behind the bootstrap. Like suppose you have an electron, let's say an positron, they interchange, let's say a photon, and they scatter. This will be interchanging a photon in what's called the T channel. This can be reinterpreted as a Coulomb potential between electron and positron, and that Coulomb potential gives rise to the positronium. And the positronium should be seen as a bound state in the S channel. So here should have some positronium that presumably some like this, but some sum of ladder diagrams or something, and it will appear in the S channel. Now, in the strong interaction, there was this observation that turned out not to be true, but from for the actual QCD, but in principle could have been true, where you have that if you have two pions, they can scatter by interchanging a row meson, and this interchange of the row meson gives rise to a potential between the pions. This row meson is a resonance, it's unstable, but you can still think of this diagram in the T channel. Now, in the S channel, you can have, because of this attractive force that the row produces between the pions, you can form a quasi-bound state of a resonance, which is a row itself. And so the idea of the bootstrap is like chicken or the egg. The row is a resonance that gives an attractive force to the pions, and this attractive force produces a resonance, which is a row itself. So here are two different things, photon and positronium, but this will be the idea of the bootstrap, that you sort of have some self-consistency of the S matrix that you can only, for example, sum interchange of particles in the T channel and automatically will give you the poles in the S channel. Now, for the numerical values of the masses of the row and the pion, this didn't work, so the attractive interaction was not enough to form this row, and you had to add these two channels independently. But then we know that this type of ideas worked in string theory or led to string theory and things like that. So this is some sort of historical note. And what we're going to be interested today, just for simplicity, we're going to consider a simple problem of scattering of a single type of particle. And if we insist on thinking about pions, I'm going to think about scattering of pi zeros or pi naught, but this is any scalar particle. So if you have a scalar particle, you can scatter it, and I'm going to write the basic formulas for the S matrix. So we have again the Mandelstam variables, which now are non-trivial because we're in higher dimension in 3+1. So this is the total center of mass energy square. I think I changed the definition of T with respect to yesterday. And they are not independent because S plus T plus U should give, if you add all this, you get 4m squared. I'm just going to put 4 because I'm going to use the mass of the pion equals to 1. And the kinematics is just these things collide like this, and then they go in some other direction with the angle theta, that's the scattering angle. And this is, I'm considering only elastic scattering. So one other thing is, why do we think that this may be unique or one of these sort of rigid theories that we mentioned before? And the reason is that if we have a, well, it's just heuristic, but if I have a pure Young-Mills theory, it doesn't have any parameters. The only parameter I have is a dimension full parameter that sets the scale, lambda QCD. That's the same if I add massless quarks. And if I add massive quarks, the only parameter I have is the mass divided of the quarks divided by lambda QCD, which I can convert into mass of the pion, let's say, divided by lambda QCD. And so I have just a single parameter that determines the theory up to, well, the number of colors, and the number of flavors is here given by the number of pions that I consider. for 2 flavors, I need 3 pions. And so that means that we have a theory with basically very few, like none or 1 parameter, and so it probably has some distinguished position in the space of all possible S matrices. However, how to find it, that's the main question, and I'm not gonna do that today. I don't know how to do it. So what I'm gonna try to do is to characterize the space of all allowed S matrices or scattering amplitudes. So let me do once again a review of standard quantum field theory, but that's the same as in usual quantum mechanics. For each channel that here is just characterized by angular momentum, we have an S matrix, SL of S. This S matrix is just a complex number that you can write it eta L e to the 2i delta L, for example. So if there is no particle production for this energy, then this is just a phase. This delta L is what we know as a phase shift. And this tells you the non-elasticity. And for pi 0, in principle, you could create here pi plus, pi minus. So it won't be, you can have particle creation. Okay, so with this SL, we can define the so-called partial waves, and there are different conventions. One convention will be defining some function HL like that. These are just functions of S. And the condition that the S matrix is less or equal than 1 converts into the modulus of HL squared is less or equal than twice the imaginary part of HL of S. And with these formulas, we can construct now an analytic function of S and T. And that goes as follows. So I can define amplitude, so which is, okay, this will have a cut in the S-plane, have a cut from 4 to infinity, same as before. And I'm gonna first define it right above the real axis for S bigger than 4. So this is the physical scattering, and I'm gonna sum over L. L in this case is even because I have identical particles. And you define it in this way. And then you analytically continue to the whole complex plane, HL of S times and the Legendre polynomial, 1 plus 2t over S minus 4. And this combination is just the cosine of the scattering angle, if one does the calculation. But this defines a function of t and s that one can analytically continue for, in principle, any s and any t. And it has cuts for s, a cut for s bigger than 4, the same as we said before, k goes to minus k, or you have some time reversal that gives you this jump. Then it's crossing symmetric. One can see that crossing symmetry here simply reduces to interchange S, T, and U. And therefore, it has to have a cut not only for S bigger than 4, but for T bigger than 4, or for U bigger than 4. So for fixed T, suppose T is not real, but not bigger than 4, then this cut, remember S plus T plus U is 4. So the cut U bigger than 4 means that S plus T will be negative. So there will be another cut here going up to minus T. And if T is 0, goes all the way to 0 as in 2 dimensions. Okay, so we have then an analytic function of ST, and I can add U, but it's not an independent variable, but sometimes it's convenient. And this is completely symmetric, and the interchange of S, T, and U. And one question is how to write the parametrization of such a function. And the most common one used is the so-called Mandelstam representation. It's not proven that it can always be written in that way, and that means that it's not proven that these are the only singularities that the scattering amplitude has. But if you assume maximum analyticity, this principle that we're not going to put singularities unless we are required by the physics, then we can assume the Mandelstam representation, and that's what we usually do in the numerics. Not everybody does that. Some people try to do more generic representations, but this is, I think, is pretty good. So if I insist to put ST and U, the Mandelstam representation is as follows. Depends on how many subtractions we have, but I'm gonna do a simple case. So I will have a constant, then I will have a single variable spectral density, sigma of x. And I'm gonna put here 1 over x minus s plus 1 over x minus t plus 1 over x minus u, and this is obviously symmetric and the interchange of st and u. And also this is an analytic function of st and u, except that it has a cut for for s on the real axis for s bigger than 4. If I above the real axis, so s minus I epsilon, 1 over this, I can do the principal part of 1 over x minus s plus I pi delta of x minus s. So although the sigma is real, this function has an imaginary part on the real axis, and if you go from above to below the real axis, you have a jump, which is precisely sigma of s. And then I have a double spectral density, which also has to have cuts from 4 to infinity. So this is rho of xy. Then I have here a 1 over x minus s, y minus t. So this term has a cut for s bigger than 4, t bigger than 4. And then I have y minus u plus 1 over x minus t, y minus u. And if I have isospin, we need to consider a isoscalar, symmetric, antisymmetric. So I have 3 such functions that we have more spectral densities. And so this is the Mandelstam representation. And the purpose then of the Bootstrap will be to study the space of such functions. And any physical theory which contains some scalar field that can interact with itself should have a scattering amplitude, the elastic amplitude for that scalar field, given by some f naught, sigma, and rho. Phi to the 4th theory will have something like that, and QCD will have something like that, where these are pions and so on. And the main problem that we don't know how to solve is how to identify the corresponding point in the space of allowed amplitudes. Allowed amplitudes, so this is this 1f satisfies crossing and analyticity, and the thing we need to impose is unitarity. That means we need to take this, suppose f naught, sigma, and rho, and then compute the partial waves from this formula. And then once you compute the partial waves HL of S, we need to impose this condition. And that gives restrictions on the possible values of rho and sigma of the spectral densities, and that's the space we want to understand. And in that space, we will find, as I said, any physical theory that we could have, consistent physical theory, and we need to identify the one of our interest. Okay, so that's more or less what I wanted to say. So now I'm going to describe some calculations to show you how we go about studying this space and some particular properties that it has. These are a bit long, so I'm not sure I'm going to do all of them, but they are lengthy, but based on some simple considerations of analytic functions. So the properties I want to show, which are already known from a long time, but one is how the behavior of the partial wave is for large L. The other thing is that if unitarity is saturated for some energies, that means I don't have particle production. The typical thing is, for example, if I have 2 particles and there is no cubic coupling, I have to create 4 particles. So I will have a elastic scattering before the 4 particle threshold. That means for S less than 16. I will have elastic scattering and unitarity saturation. Then this implies that the rho vanishes in a certain region that we're going to compute. The spectral density in certain region. And this region is bounded by what's called the Mandelstam curve or the Landau curve. It depends on both names are used sometimes. The other thing I'm going to show is an extension of this is what happens if unitarity is saturated at all energies. And that means that I have a theory with no particle production. The 2D nonlinear sigma model that we described last lecture was a case where there was no particle production. But in this case, in 3+1 dimensions, there is something called the Axe theorem that I'm going to try to derive if I have time. If unitarity is saturated at all energies, then you have a free theory. So the free theory is the only theory that saturates unitarity at all energies, so has no particle production. And that's another challenge for the Bootstrap, because although it's not necessary, when we map this space and we look at the boundary of the space where we can find concrete S matrices, then tend to saturate unitarity and have no particle production. But that's not allowed in 3+1 dimensions, and one challenge we have is how to describe particle production. Now, curiously, if you look at pion scattering, it tends to saturate unitarity more than one might expect. So it looks like a pion scattering likes these solutions that saturate unitarity to higher energy. So production of 4 pions is suppressed, I guess, in QCD.
I have a question.
Yes.
Martin. So if you saturate unitarity, you said that at all energies, you said that it'll imply a free theory. What about integrable systems? I mean, suppose I have an integrable theory.
Yeah, I don't know any integrable theory in 3+1 dimension.
I know, but
yeah, in 2 dimensions
possible.
you can do it. So, and the integrable theories, as you say, is an example. But in 3+1 dimensions, I don't think it's possible.
Yeah, it's not possible. There's a theorem that says it's not possible. Because
this is this theorem here, so called Axe theorem, I think. Yeah. But okay, theorems always have some way to, physical theorems have a way to avoid them, but as far as we know, that's the situation.
Integrability.
What is the theorem? What is the theorem, please?
Called Axe theorem that if unitarity is saturated at all energies, then the theory is a free theory. That's the theorem. It's called Axe. And I'm going to prove it now, I guess, using the Mandelstam representation, but then you can also prove it without using that, using more like axiomatic field theory. But again, one should always be careful with this proof, because there could be some loopholes or something. But as far as we know, as I know, there is no theory that in 3+1 dimensions that has no particle production. Okay, so how do we go about looking at this? So these things I'm going to describe are just based on simple considerations of conversions of series. And I'm going to use 2 results which are not hard to prove, but I'm not going to prove them, and they can be derived just from this formula for the Legendre polynomials. And this formula is a series, a power series in T, and we know that the power series should converge up to the nearest singularity, and the nearest singularity you can find it from this square root, and so you find that this series converges whenever the modulus of Z is less or equal to 1 plus t squared over 2t. And a convenient way to write this is to write t as e to some alpha, so that it becomes cos of alpha. And so I'm going to write this formula that I need. If I sum some coefficients with some Legendre polynomial, some cos mu, this is finite or less than infinity, so the series converges is the limit when L goes to infinity of modulus of AL to the 1 over L is e to the minus alpha, some constant, and the modulus of mu is less than alpha, where mu is this thing. So this is just, you can derive everything from this formula here. And this is the thing I want to apply to prove these things I was saying in the context of the Mandelstam representations where things are easier. Okay, so then we have this other formula that the scattering amplitude is this. Sum over L, and L is even here, but that doesn't affect the conversions. HL of S, and this is PL of cos mu, let's call it, where cos mu we say is 1 plus 2t over S minus 4. And so the first observation is that this series expansion corresponds to an analytic function of t. It has a cut for t bigger than 4, and that means that that's the nearest singularity. So this function this series should converge whenever t is less than 4, and so the borderline is when t is equal to 4, and that means that cos mu, which I'm gonna call it mu cos alpha 1 of S, is equal to if this t is 4. This is just S plus 4 over S minus 4. And from the condition we had before, then we, for these conversions to be true, we need to have that the partial waves to 1 over L for given energy S, center of mass or square of the center of mass, has to be smaller than this. Otherwise, this series that will not converge for t less than 4, and it will violate the condition that this is an analytic function that only has a singularity, which is a cut for t bigger than 4. And so this gives me the behavior of the partial waves for fixed S and a large angular momentum L, and this is saturated when this is equal to e to the minus alpha 1. And this is, if you do the algebra, this is when this is square root of S minus 2. And we usually use this factor in the numerics as a overall factor. So we multiply the partial wave by this before doing the numerics. That's just a trick for the numerics, only useful if you actually do some numerics. But if not, this is just, so this should be smaller than this. But this means just saturate. This is the biggest it can be. Okay, so how do we proceed now if unitarity is saturated? So remember, if unitarity is saturated, then the imaginary part of HL of S should be 1/2 modulus of HL of S squared. That's if for some energy S, unitarity is saturated. But that means that if I do the imaginary part of F, so I put imaginary part here, the imaginary part will, if modulus goes like e to the minus alpha 1, the imaginary part will be e to the minus 2 alpha 1. So the imaginary part will converge in a much larger range of t, because the imaginary part will be like the square, so it will be smaller. However, if I look at the imaginary part in the Mandelstam representation, it will still have a cut for t bigger than 4, and that's incompatible with these conversions of the series. And the only way to make things compatible is to say that the rho is 0 in the corresponding region. So that's the reasoning, and the next reasoning will be that if this unitarity saturation happens for all S, then the spectral density is basically 0 in a range, If it's 0, then the imaginary part will turn out to be 0 in a range. And if the imaginary part is 0, then the modulus is 0. So the HL, the partial wave, is 0 itself. And because it's an analytic function, if it's 0 in a segment, it's 0 everywhere. That means that the theory is just a free theory. So that's the strategy we're going to follow. I mean, this is all the old stuff, but I'm trying to use what people did in the old days and use it to characterize this space and give you some flavor of the type of calculations we like to do. This also gives some hints of how to proceed with the numerics. Okay, so maybe I'm going to write some formulas that do what I just said. One is that if I sum the imaginary part of the amplitude, this should converge, as we said, in a smaller region of, in a larger region, sorry, because this is these are smaller when S, for that S unitarity is saturated. So this should converge when mu is less than 2 alpha 1, because it's like the square. And if you look at the Mandelstam representation, remember the imaginary part came from the delta function, so you get a sigma of S plus integral between 4 and infinity, dy rho of sy. This S here is from the delta function. And then we have 1 over y minus t plus 1 over y minus u. And I'm going to define a value of t is a 2. People usually call it t2 of s. This is the cos mu. And this, I'm going to, by definition, call it a cos of 2 alpha 1 of s. And that means when t is smaller than t2 of s, this series converges, doesn't have any problem, and defines, remember, cos mu is 1 plus 2t over s minus 4. So this defines an analytic function in the region t less than t2 of s, but the right-hand side is an analytic function of t that has a cut for t bigger than 4. And this is larger than 4. And so the only conclusion is that rho, this part has to be 0. So rho of sy should be 0 for S saturating unitarity, and y smaller than this t2 of s. Otherwise, the right-hand side has a cut and the left-hand side is analytic. So that's the reasoning. And if there are no other particles, we need to saturate unitarity for sure between 4 and 16, because you have to create minimum of 2 extra particles. So we have 2 particles go to 4, and we need enough energy to create 4 particles. So energy squared will be like 16. So for S between 4 and 16, and y less than this T2 of S, we should have that rho is 0, and this can be rewritten in a simple way, S minus 4. Okay, so that's the one result, and it's not particularly illuminating, but kind of useful. And so I'm gonna now draw it in a picture. So if we have some x and y, and I have 4, this is 4. In principle, the spectral density has support in all this region, but if unitarity is saturated up to 16, then you have some hyperbola like this, and by crossing symmetry, you have, sorry, this is the hyperbola that we have, and this is the one crossing symmetric, interchange of S and T, and this rho should be 0, should be 0 here and here, and by crossing here. So in this region. Now it turns out here it should also be 0, but we cannot prove it with the way I did it today, but that's not so important. So we need, that's if unitarity is saturated. Now what happens now, that's more physically interesting, if unitarity is saturated at all energies, so all the way to infinity. So suppose no particle production. So that means that there is no particle production from here all the way to infinity. And that means now this should be 0, not only here, but so remember, I have to take here a segment where I don't have particle production, and I look below this curve. But now this segment is the whole real axis, so I will have to have a 0 all here also. So in all this strip, I will have to have a 0. Rho should be 0. So no particle production, then rho of Sy is equal to 0 for S bigger than 4, which because we say for any S there is no particle production, and Y less than 16, let's say. Actually more, because it should be below the hyperbola, but I only need this. Because if I do this by crossing, I should also have that rho of Sy is 0 in this rectangle here. If it's 0 here, it should also be 0 here. And that will be S Y bigger than 4 and S between 0 and 16. And now we go back to our previous calculation. So rho we said is 0 for any Y bigger than 4 and S between 4 and 16, but the integral is from 4 to infinity. So this rho will be 0, and this will be 0 for S between, between 4 and 16. So if there is no particle production, this term is gone, and that means that the imaginary part of HL of S for any S that is not 0, because here is where there is T dependence, should be 0. But the imaginary part is 0 from the unitarity condition. The modulus of HL also is 0, and that means that HL of S is 0 in this segment. But HL of S is an analytic function. If it's 0 in a segment, it's 0 everywhere, and that means that all the partial waves are 0 with L bigger than 2, so this is just sigma of S. But then I will have a scattering amplitude that depends only on S, but that will not satisfy crossing. And so you get that you necessarily have to have particle production, and that's one of the challenges for the Bootstrap. So then the other thing I wanted to show you is how to put some bounds for the amplitude, so we can show that the amplitude is bounded, but it's a bit also another lengthy calculation, so I'm gonna probably do it with a slide. So what I want to do now is just to write a couple of formulas about the forward amplitude, because, okay, okay, this is, so we are done with this slide. And then remember, so remember that 1 plus 2t over S minus 4 was the cosine of theta, the scattering angle, and the forward amplitude is theta equals 0, and that's the same as t equals to 0. So the forward amplitude is defined as this, and u has to be 4 minus s, because they all should add up to 4. So if I consider this as a function of s, this is called forward amplitude. Then I have the property that f is an analytic function of s that has this crossing symmetry, because if I do s to 4 minus s, I just interchange s and u, and that's crossing symmetric. And then it should have a cut from 4 to infinity. and by crossing from minus infinity to 0. So the forward amplitude has the exact same properties as the amplitude in 2 dimensions that I mentioned before. And then I can use this generalized dispersion relation with the k and put bounds on the modulus on the value of f here by integrating the modulus of k and all those things we did in 2 dimensions. So that's what I'm gonna do. But okay, so I'm gonna finish here this part, and I'm gonna jump to the slides. So let me know if there are any questions, and in the meantime, I'm gonna change to the slides.
Any questions while things are changing over?
Can you see the slides?
Them, and I'm not seeing questions, so you think you can forge ahead?
So by the slides you can see, I guess, yeah. So let me once again repeat a little bit this idea of Paulo Penedones, Toledo, Van Ries, and Vieira, that, okay, other people, that including me and others, we kind of help later to put in this way, which is that in the initial idea of the bootstrap by Chu, Mandelstam, many other people, it was that if you put enough constraints on the S matrix, and they were thinking about the strong interactions, you have a single solution. So you have a unique S matrix that is some sort of self-consistent. This idea of the nucleon democracy or things like that, hard democracy. But this idea doesn't work. You can have many consistencies S matrix. So the new approach, if you want, is to map out the space of allowed S matrices. And in 2D in particular, we found that that space, well, it's always a convex space. If you look at S matrices in a subspace of states, for example, 2 particle states, and has a boundary, and in that boundary, for example, sometimes there are vertices that correspond to interesting theories. That's not always the case, but in this space of allowed S matrices, we need to find the S matrix of interest by some extra considerations, and that's one of the things which is not clear. What should we do to find it? And in 2 dimensions, we have this, we said primal and dual approach. So in the primal approach, we take some S matrix parameterized, for example, by a polynomial, and the more coefficients of the polynomial, the larger the space we map. The other was the dual, where we have these Ks, which essentially are like Lagrange multipliers that impose a constraint. And the more Lagrange multipliers we put, the more we restrict the space, and that we can converge into the space of allowed S matrices from inside and from outside. That was in 2D. And in 4D, this is the formulas I was writing. So you have some collision, and you have the Mandelstam representation for the scattering amplitude, analytic function of ST and U. This is, okay, what I just mentioned. And this is the calculation I was trying to show you. This goes back to the 70s by Chang and Mao. And it's based on this forward amplitude, although here we did it, although this idea was from Chang and Mao, we just modified by adding this K, this generalized dispersion relations, as I like to call it. So the idea was that if you have want to evaluate this, if you want to evaluate the forward amplitude at some point S naught, which could be 2, the symmetric point, then you can do it by putting some function K that has a pole there and could have cuts, and the F becomes just the integral of this imaginary part. And sorry, this is a different calculation. Sorry. Well, then you can do it like this, and then you can use the same thing as before, that the modulus of the imaginary part is less or equal than the modulus. and the modulus of HL is less or equal than the square root of twice the imaginary part. And here I'm doing a different calculation, sorry, that the one I wanted to show, but it's based on putting bounds using the so-called scattering length. So the scattering length tells you how the scattering behaves when you go at very low energy. So low energy, that means 4m squared plus a little bit. And one can see that there is a formula for the scattering lengths based on dispersion relations that also depends on the imaginary part. And the idea is simply to use that the scalar product between two vectors is less or equal than the product of the norms. So I'm going to just sum an integral. So I'm going to consider the sum over I to be the sum over L and the integral over S. And here this I will consider to be the scalar product, and this to be the norm square of one of the vectors. And so this scalar product will be less or equal than the norm of U, which is square root of A2 times the norm of V. And what's V? Well, I should square this and divide by this. That will give me what V is by definition. But if I square this and I divide by this, the imaginary part of HL goes away. And that means that the rest gives me some factors. And that means that if I have a given scattering length, which is determines the low energy behavior of the scattering, then I have a bound on the function at some unphysical point here S0. And this bound is not very good. So here what we did is this parabola is plotting this bound. So it's very simple to obtain. Is this parabola, and this parabola here is the actual bound that you do numerically by putting a set of analytic functions and doing all the numerics with a large number of coefficients. But it's still pretty good considering that we didn't do once again, we didn't do here anything numerical except this integral. You have to put some test function here and do the integral, and that gives this bound. And in the same way, you can just bound this absolutely without having to put given scattering length, so that you can also find a bound using these techniques of generalized dispersion relations. Okay, so now I'm going to show results from the numerics just to illustrate some points. The numerics here, I'm trying to evaluate the scattering amplitude as the most symmetric point where all the Mandelstam variables are equal. And once again, we do the primal problem by proposing more and more general scattering amplitudes, and the bound goes up. And then we do the dual problem where we put more and more constraints and the bound goes down. And here we do an extrapolation with a number of coefficients. For some reason, the dual approach will converges faster to the maximum, the value that this scattering amplitude can have at this point. So this, once again, we're characterizing the space of scattering amplitudes. That means that if I have any scattering amplitude between scalar particles, elastic amplitude, the value of the amplitude at this symmetric point cannot be bigger in that is 2.661. And when you saturate that bound, you get some nice partial waves. So these are the S waves, for example. And you get, okay, it doesn't matter here. But what one finds is that there is the maximum of the amplitude is obtained when you have a polar threshold. So we assume no poles because inside the physical sheet, because there are no bound states, but you can have a pole on the real axis as threshold. So that means that S equals to 4, and that maximizes the amplitude. And what we find is that we can reproduce the existence of that pole without the assumptions. So the blue line is assuming we have a pole, and the green dots are without assuming anything, just putting an arbitrary analytic function. It creates the pole by itself. And this is, if I have for those who remember, this is the Mandelstam triangle, but if you have the value of S and T, S bigger than 4 is physical, and T bigger than 4 is physical in the cross channel. This is the unphysical region between 0 and 4. You can try to evaluate what's the maximum value of the amplitude for any point along this diagonal. And this is the maximum. So once again, this is the primal. So you go from below and the green goes from above, and they converge into that blue line. So the blue line gives you the maximum value that the amplitude can have for any value of S naught in this triangle. This black diamond points here were some results from Lopez and Menessier from the 70s. There is also some new results by Guerrieri and Sever that agrees with our results here. So everything seems to be consistent. Now, one problem is that QCD is weakly coupled. So because the pions are, not the QCD, but the pions themselves, they have derivative couplings because some pseudo-Goston bosons, and that means that at low energy, the coupling is small. And that's another challenge. That means that this maximum here for the scattering amplitude of QCD will have a much smaller value. So we don't find in this plot like any of these points would correspond to QCD. So it's just exploring the space. And the same way you compute the maximum, you can try to find the minimum. Okay, this is just a zoom in. So this is the minimum that you can have. So between this curve and the other curve above is where the value of the amplitude has to be. The minimum is much more challenging numerically, and so we have this sort of more broad region of confidence region that the maximum is somewhere in this region, but we don't have like a sharp line like for the minimum. So it's in this region, not the same as the maximum. And the numerics break down when you get closer to what's called the large Mandelstam triangle. But up to here, things seem reasonable. Once again, these are the old results, the diamond. And one interesting thing we find is that the amplitude that minimizes the value, so for each value of S, we have an amplitude that has the smallest possible value, but between 0 and 2, so in this part of the Mandelstam triangle, it seems that the amplitude that minimizes is always the same. When you go from, or at least numerically, it's the same. When you go beyond 2, the amplitude that minimizes for each point is different. So that's another result. So once again, these are all seems to be scattered results, but one is trying to map all the space of all possible amplitudes. And once we understand better that space, and I think the numerical and mathematical techniques are not there. So it's not a well-developed area of math finding these analytic functions with constraints. And this is the case of 3 pions, so it's more similar to the 2D in that sense. You have a isospin 0, 1, and 2 that before it was called isoscalar, antisymmetric, and symmetric. And you have then 3 different amplitudes corresponding to 3 different scattering matrices. These 0 and 2 have angular momentum even, and 1 has angular momentum odd. And they can be written in terms of a single function A. And one can, for example, evaluate it at some point here and see what are the allowed values of A. And once again, you get these regions with vertices like we have in 2D, these convex regions with vertices. And what we can see is the vertices corresponds to having, for example, a polar threshold. And then when you go to this other side, this pole disappears. So the vertex is produced by a pole reaching, coming from outside the physical plane and reaching the physical line. However, none of these vertices correspond to QCD. once again, QCD is kind of here in the middle with the small values of A. So that doesn't mean that it's not at the boundary, because this is a section of the space. So if I have a cube and I put it, I say, on stand it on a vertex and I do the shadow, some vertices will appear at the boundary, but some other vertices will be in the middle. So it could be that there is another direction here where I can go, and QCD will be at the boundary. So it will be easier to figure out. But that's all the things we don't know yet. Okay, so that was more or less what I wanted to say. So I think there are maybe 15 minutes. So I have some discussion points that you might want to, or we might want to discuss. So let me say some things about them. So one is how do we incorporate particle creation? So we saw that particle creation is necessary, but these S matrices that we compute that are at the boundary of the allowed space are tend to saturate unitarity. Now, this argument was using conversions of the series, so it seems possible that you can push particle creation to large angular momentum or things like that. So it could be that you can have numerically S matrices that saturate unitarity at all energies that you are considering. You never consider up to infinite energy or arbitrary large angular momentum. So that's possible, and then we are not going to find, unless we put on purpose that there is particle creation. Then I think these questions already were raised yesterday. So what theories are at vertices? Should we always have integral theories? But that's not necessarily the case. One naive guess is that are theories that have very few parameters or are unique in some way, but that's also not clear. The other question is how do you incorporate the UV properties of the theory in the low energy bootstrap? So we said that the ideal situation, somebody will give me a gauge theory with some n and number of flavors, and that's the UV description. And I have to have some way to incorporate that into the bootstrap. And Joao Penedonet has some nice ideas of trying to incorporate in the UV, you have a conformal point with some central charge, and try to incorporate that into the bootstrap. So the other thing is if we look at pions, we said that we have a dimensional parameter, which is the same mass of the pion divided by lambda QCD. And how do we incorporate that scale in the bootstrap? So in the bootstrap, we didn't put any scale other than the pion mass. Naively, one way would be to incorporate nucleons, for example. So you will have a pion and nucleon, and then the ratio between the mass of the pion and the mass of the nucleon would be the parameter that will give you the correct scale. And but the question is, I mean, nobody did these nucleons. Well, in the old days, people had the pion nucleon interactions, but in this new approach, it seems to be quite difficult to do. Nobody did that. And so, for example, if I want to determine the raw mass, I need to put some scale. And how do I put it? Do I need to put a nucleon, or can I put just some scattering lengths, or put some information? Or some people just put the mass of the raw as extra information and see what happens. And well, this is maybe a technicality about the A2, but then the last point is to make connection with this effective field theory approach. So the standard approach to low energy physics is to write the most general Lagrangian with all the symmetries, and then you have a set of coupling constants. The more coupling constant, the larger the energy you want to look at. And so with two coupling constants, let's say you can already have some good description of low energy. This is like the Scherm-Lagrangian, for example. And that's the approach that Albert and Rastelli took in this recent paper. So they use that, and then they compute scattering and put bounds from unitarity, crossing and unitarity on the couplings. And they found this vertex that they claim could be large in QCD. one thing is that they didn't put the unitarity constraint, they just put that the imaginary part should be positive. So that's, and that should be good for small coupling or for low small couple theories, because the modulus square of the amplitude should be basically 0, so you will have just the condition that the imaginary part is positive. And some people are trying to do the same as they did, but with the full unitarity constraints. Okay, so I don't know, I guess we have 10 minutes, but maybe since it's the last lecture, I will be happy to answer questions, or you can just take a longer break. So let me know how we're going to do.
Thanks, Martin. I think as we do have 10 minutes for questions, we should be able to get some before taking a break. Does anyone have anything immediate to ask in the room?
Or some comments, or it doesn't have to be questions.
Okay. I don't know if this, hello? Hi.
Yes, yes.
If other people have questions directly, they should take it first, because this is really a question of a new direction, and I wonder whether your techniques could be bent in this form. So it's really not quite your talk, but I keep thinking about the fact that we believe that there's a large NQCD. Now, of course, it has some simplifications which are very much like a conformal bootstrap. It's meromorphic, right? So you have a meromorphic amplitude, and you would think, gee, you know, it's sort of like a conformal bootstrap. Its data is entirely in terms of the poles and the coupling constants. That's the data for the whole thing. The other advantage is that when you're pi scattering, there's no threshold. So it's only the first term of the chiral Lagrangian, just the Born term. So you don't see any effect of the light pions coupling. There's a derivative coupling. The only amplitudes are mesons. There's no other things. Isospin is trivial because just like in a gauge theory, all of the spin indices are outside. So you just have just have tau matrices outside in the sort of core amplitude that strips off. So at that point, you know, you've got a very simple object. Now I agree that you've got to replace, you don't have unitarity, but of course the replacement for unitarity was to take rays off the real axis where Reggie behavior gives you a phase, and the power of that Reggie behavior is sort of implicitly the unitary bound. I mean, it's, so I mean, I just wonder whether this could be somehow closer to the conformal bootstrap, and you might do something. You would do this, by the way, there's no problem of analytic continuation because there's no cuts at all. So you can go to the Euclidean thing.
Poles.
They're only poles, so everything is absolutely trivial.
Yeah, one question. I don't know if you should put the
so I mean, there's a lot of
constraint that you some poles on the S channel, you should get the T channel. That will be a
I mean, that's exactly true, of course, of the Veneziano formula. So that's what you hope to get. That's
no, but if you put that as a constraint and you use the bootstrap with that.
But that is the constraint of the n equals infinity QCD. That's
yes. So that's probably so it's a different bootstrap, but I think it should be possible.
And by the way, another thing is that it's planar and it only has two poles in two channels. It's absolutely no singularities in the cross channel.
Richard.
So I just wonder, can you think of a way in which this, or would it just be terrible because you wouldn't have this unitarity?
Richard, this is what Rastelli did.
What?
This is what Rastelli did. This is exactly how they did it. They did large n, pion, sigma, model Lagrangian.
So what do they replace? I mean, from the context of this approach, what replaces unitarity?
They state that the amplitude just has poles at the masses of things like rho's and stuff like that. And then they put a cut below the effective cutoff, which is the mass of the extra particles. And then they try to find S matrices that are compatible with that.
They don't use any asymptotic condition.
Convergence of some spectral form factor or something like that.
See, I mean, you can't write a dispersion relation without an asymptotic conversion. So the
well, they assume that it converges.
So they must assume some asymptotic condition.
Yes.
So that would replace, I would think, the unitarity constraint.
Yes. And this is what they did.
Okay, but it's very different technique than this, or no?
No, the once they get it, they use some type of semi-definite programming to find the regions. Yeah, read their paper. Yes, they make progress on it. Right. So the way they write it is that instead of doing the S matrix, you have just 3 level diagrams. So no, because it fails unitarity in some senses. At large N, this is a way. Right. So that's what the effective field theory is. It is an amplitude, and you read the vertices and the poles, and then you can use that to reconstruct. No, there is space-time in the sense that when you have the poles, you associate them to real particles, and you write an effective field theory of the pions, which starts with the usual sigma model, plus effective couplings that reproduce whatever you have. But the point is that they don't know what the spectrum of higher particles is. So what they do is they bootstrap the low energy effective theory of the pions. They put bounds on that. Right. It's the one of Albert and Rastelli. This is what they've been doing. They just pulled it out 4 months ago, 3 months ago. So I saw Rastelli give talks about it. And this is what they're doing. That's why they did it. So, Martin, do you have?
Hey, how are you?
Any, I mean, are there any numerical issues that make it hard to converge that have to do that require, let's say, new software in some sense, or?
No, I think well, there are some couple of tricks that you have to do, like I was saying, rescale the partial waves and some things like that. But then it's not no, numerically is quite robust. The thing is you have the allowed space, and how do you say where QCD is? So you need to add some extra information. Depending on how much you add, you can claim you are cheating or you are claiming you are solving QCD. So the idea is what the minimal amount of information you want to add to, for example, in 2 dimensions, you have this space of allow the here, and I need to know in which, suppose from the origin, in which direction is the integral mode. So I said the integral mode is in this direction. So I found this point, and this point is the Hull's matrix, just based on one. So by knowing the angle, let's say, I just know one number, and I can compute the Hull's matrix. Now in QCD, the problem is first that if we plot regions like this, QCD is not at the boundary, so it will be right here in the middle. So first is what are the correct axes that I want to do so that QCD is somewhere at the boundary, and then how do I determine which direction QCD is? Ideally, you would determine it from the microscopics, but I don't know how to do that. But at least from some phenomenological, suppose you say, well, if somebody gives me the experimental value of the scattering length, then I can tell you where this is. But I mean, that's not how it works, but that kind of thing. So numerically, I think it's fine. We can put the experimental. So if you take the experimental phase shifts and you put them in the numerics, they fit very nicely and satisfy all the properties. But the question is if somebody gave you a different experimental phase shifts, you will also fit it into the numerics. So how do you know which one is correct? And so maybe the question is what between all the scattering analytic functions, what special property QCD has that the others don't have? And I guess that's the question one would like to answer. But numerically, we can put the experimental thing and fits everything. We can plot these regions. Numerically seems not a big problem.
Maybe I will ask one quick question for us to wrap things up. The idea you mentioned of incorporating nucleons into this whole procedure seemed appealing to me if we want to get at phenomenological QCD, but you mentioned that there are problems with doing that in your new approach. I wonder if there's a nice story you could tell about what those problems are or how they.
Well, we did try it. I think Joao tried it, Penedones, and he said it's too complicated. But maybe we should try it. Yeah, I think we should sit down and write the program and see what happens. Yeah, that should be. Yeah, I think that should be the. If you think, how is it called, the most conservative approach will be to put pions, nucleons, and put the correct ratio between the masses. And that should be all that you need in some sense. But yes, well, first, obviously, the nucleons are fermions, and you have a bunch of different amplitudes, NN bar to pion nucleon to pion nucleon, and you have all these crossings, so you have a lot more functions. But in principle, yes, it's possible. I mean, yeah, in principle, it's possible. In practice, I think it's a bit complicated. And although, okay, I was telling, David, that this numerically is fine. It's also kind of at the edge of what can do. So if you put a double or triple the number of functions, then I don't know if one can do it easily.
Your mention of NN bar.
Yes. I cannot hear now. You said I mentioned NN bar and then I didn't hear anything else.
That microphone is running out of battery.
Oh, yes.
Yeah, NN bar, if those annihilate given the physical mass ratio, you could have many pions coming out.
Yes.
4, 6 more.
Well, if you have pion nucleon to pion nucleon, you get NN bar by crossing. So you should stay within that sector. But of course, probably the dominant process creates many pions.
Give one last call for other questions, either here in the room or remotely on Zoom. And not seeing any, I think we should thank Martin for his 3 very interesting lectures on the Bootstrap.
Okay, thank you very much. And
we'll have a break now, and I guess we'll see you again for a research talk next week.
Next week, yeah.
We'll do that. Thanks again.
Okay.